Okay, this is exercise 5.2. I'm going to do some of the problems from Q2, some of the odd numbered problems. The even numbered problems are assigned for homework. Now the difference between 5.1 and 5.2 is an additional rule gets added, namely the conditional elimination rule. Okay, and again I'm using the greater than arrow just because I'm on a keyboard. This is equivalent to the horseshoe in the text, this horseshoe. And again I'm using the ampersand here instead of the dot because again it's on the keyboard. So basically same idea. We've still got these four rules that we looked at with 5.1. Now we're adding an additional rule, conditional elimination. Now conditional elimination requires two inputs. One is a conditional, the other is the antecedent of the conditional. Remember, the antecedent is the part of the conditional that comes on the left of the horseshoe. The other part is the consequent. So if I have if P then Q, if I know that's true, and if I also know that P is true, then I can know for sure that Q is true, right? And again, this is supposed to be natural reasoning, natural deduction. So, you know, if the Red Sox win the World Series, then Boston will celebrate. The Red Sox win the World Series, therefore Boston will celebrate, right? It's a very natural inference. So we'll add that to our list, and we'll otherwise do the same, use these other four rules. Again, in the text, Q2 is listed with commas all on one line, but you have to set it up like this. You have to number the premises, and you have to lay them out one over top of the other, like one premise per line. The three dot symbol indicates this is the conclusion. Now that's not a premise. You can't use that. That's what you have to get to. That's our goal. We put it here to remind ourselves it's our goal. But we have to apply these five rules now up here to these premises to get this conclusion. Okay, that's the goal of a proof or a derivation. Alright, so let's start with number one. Okay, so we've got three premises. This is a conditional. Then we have P by itself and Q by itself. Now to get R by itself, you might think we can just do conditional elimination. But to do conditional elimination, you need a conditional and the antecedent. So the antecedent of this conditional is P and Q. It's that whole thing, that whole conjunction. So we cannot apply the conditional elimination rule until we have the entire antecedent. Luckily, though, we can get the antecedent because if you remember our conjunction introduction rule, if we have P by itself and Q by itself, we can put them together and do a conjunction. And in fact, we do have P by itself and Q by itself. So that's conjunction introduction of 2 and 3. So remember, the introduction rules introduce that operator. So if I see on a line this says conjunction introduction, I should be able to look to the left and I better see a conjunction there. Okay? Because that's what introduction means, is I'm introducing on this line that operator. Okay, so now I have the antecedent. I can get the consequent by the conditional elimination rule that we just looked at, right? So conditional elimination. Now it requires two inputs. It requires a conditional, so we have that on line 1. It requires the antecedent of the conditional, so the antecedent is P and Q. We have that on line 4. So conditional elimination, lines 1 and 4 gives us R. And we're done, because that's the conclusion. So we stop the proof once we reach the conclusion. Okay, let's look at number 3 then. Again, we got a conditional here, and in fact, the consequent of a conditional is our conclusion. So it looks like we want to use conditional elimination. But to do conditional elimination, remember you need conditional plus the antecedent. So the antecedent here is not A. And if you look on our lines, we don't have not A by itself anywhere. So we cannot do conditional elimination right away. But we do have not A here in a disjunction. So if we could eliminate that disjunction, get not A by itself, then we could do conditional elimination to get not B. So let's go back and look at disjunction elimination. Disjunction elimination tells us if we have a disjunction and the negation of one of the disjuncts, we can derive the other disjunct, right? And that can work either way. So again, remember, like heads or tails, not heads means tails. Heads or tails, not tails means heads. Okay, so here we have a disjunction and we have the negation of one of the disjuncts, just like we need. So that gives us the other disjunct. So that's disjunction elimination. Requires two inputs, a disjunction, that's on line 2, and the negation of one of the disjuncts, that's on line 3. So now we've got not A, and we needed not A to get not B by conditional elimination. So conditional elimination, again, requires two inputs, a conditional, that's on line 1, and the antecedent of the conditional, which is on line 4. And again, that's it. We're done, because this tells us we need to get to not B, and we got to not B. So remember, what this shows, what this proof shows or derivation shows, is that the original argument is a valid argument, right? Because if these premises are true, the conclusion does indeed follow from them, right? Now, the way this works is, if you think about each of these rules is in itself a valid argument, right? If P and Q are true, then the conjunction is true. If P is true, then the disjunction is true. If the conjunction here is true, then P is true. So all these are valid inferences. So if I make a valid inference every step of the way, I'm preserving the truth, right? Because remember, validity means if the premises are true, then the conclusion must be true. So if these premises are true, not A is true. Why? Because this is a valid inference rule. And if these premises plus not A are true, then not B must be true, again, by this valid inference rule. So the whole derivation shows or proves that the original argument, namely this, was a valid argument. Okay, that's what we're doing. We're using derivation to prove an argument's valid. It's a different method from truth tables, but it has the same effect of showing an argument to be valid. Okay, so jumping down to number 4, here we've got a disjunction, we've got a double negation, we've got a conditional. The consequent of the conditional is our conclusion. So again, if we could do a conditional elimination, we could get our conclusion. But to do a conditional elimination, you need the antecedent of the conditional by itself, and we do not have Q by itself. But we do have Q here in a disjunction, and again, same as up here, if we can get rid of the disjunction, we can get Q by itself, and fortunately, we can do that by disjunction elimination. And remember, disjunction elimination takes two things. It takes a disjunction, which we have on line 1, and the negation of one of the disjuncts, right? Not P is a disjunct, so the negation of that is not P. So disjunction negation on line 2 gives us the other disjunct Q by itself. And now that we have Q by itself, we can apply the conditional elimination rule to get not R. So the conditional elimination rule again takes two inputs, a conditional, line 3, and the antecedent of that conditional, which is on line 4, and it gives us as output the consequent of the conditional, which is our conclusion. Okay, jumping down to now number 7. We want to get B, that's our conclusion. Where does B occur in the premise? It's in a disjunction. So if we got not O, then we could do a disjunction elimination to get B. But we don't have not O. Well, here's not O and a conditional. We could get not O out of this conditional with conditional elimination, but to do that we need the antecedent of the conditional, which is L and M. We don't have that. We do have L by itself and M by itself, so we can put those together using the conjunction introduction rule. Right? Line 1 is L, line 2 is M, so the conjunction introduction puts those together into a conjunction. So now we have the antecedent of this conditional, so we can apply conditional elimination to get not O. Remember, conditional elimination takes two inputs, a conditional, that's on line 3, and the antecedent of that conditional, which is L and M, and that's down here on line 5. So 3 and 5, applying the rule conditional elimination gives us not O. And then we can get our conclusion B by disjunction elimination, right? We had B or O here. Now we have the negation of this disjunct. That gives us the other disjunct. So disjunction on line 4, negation of one of the disjuncts on line 6. And that gives us the other disjunct on line 7. And again, that's our conclusion. So we are done. Last one, number 9. We want W or X. Okay. So we want a disjunction. And we've got conditional, got a disjunction, we've got a conjunction. Now notice to eliminate either the conditional or the disjunction, if you go, again, look, the conditional elimination rule requires 2 inputs, conditional plus antecedent. Disjunction elimination requires 2 inputs, disjunction, negation of one of the disjuncts. But conjunction elimination doesn't require anything else besides the conjunction. So in number 9, we can't do a conditional elimination because we don't have not X by itself. We can't do a disjunction elimination because we don't have the negation of either of these disjuncts by itself. But we can do a conjunction elimination. Right? So we can get not V by conjunction elimination of 3. And we can get not X also by conjunction elimination of 3. Right? Notice we only use one number because it only requires one input, namely a conjunction. Okay, so now we have some stuff to work with. Since we have not X now by itself, we can do this conjunction elimination. Sorry, conditional elimination. So we have conditional on line 1, and we have antecedent of that conditional on line 5. So that gives us, as a result, the consequent, not Y. Now, not Y is the negation of one of these disjuncts, so we can get the other disjunct. Disjunction elimination. Line 2 is our disjunction. Line 6 is the negation of one of the disjuncts. So 2, 6, and that gives us the other disjunct. Now remember, this conclusion is a disjunction. So the disjunction introduction rule allows us to put any sentence we have into a disjunction with any other sentence. So we had W, so we can put that into a disjunction with X by disjunction introduction. And that's only one number, 7, because that's all we needed, right? The disjunction introduction rule requires only one input, so it's only going to have one number after it. Alright, so that's 5.2. Again, it uses these 5 rules. I'll post 5.3 soon that will introduce conditional introduction and maybe some other rules. No, I think just conditional introduction.